Welcome back to the deep dive. This is where we dig into interesting ideas and see how they connect to, well, to our everyday world. Today, we're exploring something I think is pretty fascinating. How, advanced math and some clever algorithms are actually making essential services, like our power supply, more reliable. It's a really cool look at how data, when used smartly, can genuinely improve things for all of us. And joining me to sort of unpack all this, we've got our resident expert, always great at connecting the dots and explaining the why.
Hi there. Yeah, looking forward to getting into this one.
We also have a curious mind with us, really keen to get the basics right and help keep us all on track.
Absolutely. Ready to ask the maybe obvious questions to make sure it all makes sense.
Great. And someone who's laser focused on, the practical side of things, always asking, okay, but how does this actually work in the real world?
That's me. Yep. Keen to see the tangible results.
Perfect team. So the specific project we're diving into today, it's work by Arthur Gagg, and it uses graph theory and something called Kruskal's algorithm, the goal, making power grids more resilient. And what's really neat is it's based on a study of an actual city. So let's maybe kick off with the problem itself. How do we make sure the lights stay on, especially, when demand suddenly spikes? Our power grids are generally really robust, right? But what happens if one area, one district, suddenly needs way more power than its local substation was designed for?
Yeah, that's exactly the core issue Arthur Gagg is tackling here. That kind of imbalance, it can cause power outages. Simple
Yeah.
as that. So what you really need are fail-safes. Basically, you need backup connections, specifically interconnections between the substations. So if one substation gets overloaded, a nearby one that's properly linked up can help share the load.
Right. So without those links, those interconnections, we'd probably see more blackouts. Is that the main risk, or could it be worse, like things spreading?
Well, more frequent blackouts are definitely the immediate worry, but yeah, you're right. Inadequate connections do increase the risk of wider instability. Cascading failures aren't out of the question. Arthur Gagg's project, it proposes a really smart, optimized way to create these vital links. It's about designing that resilience right into the grid's structure. And it does this by bringing together some pretty powerful tools. You've got OpenStreetMap for the map data, Network X for handling the network structure, graph theory as the foundation, the idea of a minimum spanning tree, and then Kruskal's algorithm to actually find the best solution.
Okay. Okay, that's a lot of pieces. Let's unpack this a bit. Before we get to the final solution, we probably need to get our heads around some of these core ideas. Maybe start with graph theory itself. I mean, most people listening probably think of graphs as like charts, but here we mean networks, right? Points and lines, nodes and edges. The real power, I guess, is how they let us model complex relationships and find patterns we might otherwise miss.
So it's like taking something complicated, say a city's power grid, and simplifying it down to dots and lines just to understand the connections better.
Exactly. You're abstracting it to focus on the connections. And another key idea in graph theory is something called a cycle. Imagine you can start at point A, go to B, then to C, and then loop right back to A again without retracing your steps. That closed loop, that's a cycle. Now, not all graphs are the same. The article mentions the graph for this power grid problem is undirected and unweighted, at least initially.
Okay, undirected and unweighted. What's the practical difference? Why does that matter here?
Good question. So undirected means the connection works both ways. If A can send power to B, B can send it back to A along the same path, like a two-way street. And unweighted, that just means for now, we're treating all connections as equal, no specific cost or distance assigned yet. Later on, when we optimize, those weights like the actual cable length become super important.
Yeah.
And just quickly, there are other types too, like connected graphs where you can get from anywhere to anywhere else. Digraphs have one-way streets. Multigraphs allow, say, two different roads between the same two towns. And a complete graph has a direct link between absolutely every pair of points. It's a flexible way to model things.
Right. Got it. So graphs are the model. How do we actually, build and analyze them, especially with real map data? Is that where Network X fits in?
Precisely. Network X, usually people just call it an X. It's a Python library, a really powerful one. It makes it much easier to create these graphs, mess around with them, analyze them, even draw pictures of them. It has built-in tools for things like combining graphs or finding the shortest path between 2 points, which is obviously useful here.
Okay, Python, Network X. But how does that connect to actual maps? Like, the streets and substations in a real city.
Yeah. Good bridge. That's where OpenStreetMap, OSM, and this other tool, OSMNX, come in. Think of OpenStreetMap as like the Wikipedia of maps. It's open source, community built, huge amount of geographic data for the whole world, free to use. And OSMNX, people usually say OX, that's the magic connector.
Yeah.
It lets you pull data from OpenStreetMap, like a city's road network, and turn it directly into a Network X graph. So suddenly road junctions become your nodes, and the road segments between them become your edges. It basically translates the real world into a graph format that Network X can understand and analyze. It's pretty slick.
Okay, that makes sense. So we have graphs, we have the tools like Network X and OSMNX to build them from real maps. Now, you mentioned a specific type of graph earlier,
Right.
a tree, and a minimum spanning tree. What's that about?
Right. So a tree in graph theory is it's a special kind of graph. Its defining feature is that it has no cycles. Remember that ABCA loop. A tree doesn't have any of those. Every point, every node is still connected, but there's only ever one single path between any two nodes. No redundant connections. And a minimum spanning tree, or MST, builds on that. It's a tree that includes all the original points you wanted to connect, but it does so in a way that the total weight of all the connections, all the edges it uses, is the absolute minimum possible. So if your weight is the length of cable needed for each connection, the MST finds the cheapest way to wire everything up together without any loops.
Okay, so if we're connecting those power substations, the MST would basically show us the shortest total length of cable needed to link all of them up without wasting any cable on redundant paths.
Exactly. You nailed it. That's the core idea when you're talking about laying potentially kilometers of really expensive power cables across a city. Minimizing that total distance is, a huge deal. It saves money, makes the project more efficient. The MST concept is a perfect fit.
And finding this perfect fit, this MST, that's where Kruskal's algorithm comes in.
Mhm.
Named after Joseph Kruskal back in 1956. You called it a greedy algorithm. How did that work?
Yeah, greedy sounds a bit odd, but in algorithms, it just means it makes the best looking choice at each immediate step. It doesn't look ahead too far, it just picks the best option right now. For Kruskal's, your starting graph needs to be connected, undirected, and crucially weighted. Those connections need to have costs or lengths. The logic is quite elegant, really. You start with nothing connected. Then you look at all the possible connections you could make and you sort them, cheapest first. Then you just go down the list. You take the cheapest available connection. Does it link up two substations or two groups of substations that weren't already connected? If yes, you add it to your network. If no, meaning adding it would create one of those cycles we talked about, you just skip it and look at the next cheapest one. You keep doing that until everything is connected into one single network. There are some clever ways it keeps track of what's connected to what, using concepts sometimes called make set, find set, and union, but the basic idea is always add the cheapest edge that doesn't form a loop.
Huh. So it's like you have all the possible connections laid out, sorted by price, and you just pick the cheapest one, add it, pick the next cheapest, add it. Unless it connects two places already linked somehow, then you skip it. That sounds simple, almost.
It is surprisingly simple in concept, and that greedy strategy actually guarantees you find the true minimum spanning tree. The complexity isn't usually in the algorithm itself, but maybe in figuring out the correct weights or costs for each potential connection in the first place. Is it just distance or does terrain matter? Permits, things like that.
Okay, this is where it gets really practical then. We've got the theory, the tools. Let's see how Arthur Gagg actually applied all this in that real-world project you mentioned.
Okay, yeah. So the case study was the city of Natal in Rio Grande do Norte, Brazil. The code, which was adapted from some earlier work by Professor Ivanovich, it followed a pretty logical sequence. First step, importing the graph. They used that aux.graph from place function from OSMNX to grab the map data for Natal, specifically the drivable road network. And right away, a real-world problem. Part of the city was across a river, technically outside the main boundary, so they had to specifically grab the graph data for a key bridge and then merge or compose it with the main city graph, making sure the digital map matched reality.
Okay, so step one is just getting the basic map into the system.
Yep. Then step two, convert the graph type. As we said, OSMNS often gives you a multi-digraph, which might have multiple edges between nodes or directed edges. Kruskal's needs a simple, undirected graph, so they used a custom function to convert it. The key here was making sure they didn't lose all the useful information attached to the roads and junctions, like names, types, lengths. That all had to be carefully copied over to the new, simpler graph structure.
So a lot of data cleaning and preparation just to get it ready for the main analysis seems pretty common in data
Oh,
projects.
absolutely. Prep is often like 80% of the work.
Oh, okay.
Okay, so once the graph was tidy, step 3 was getting the locations of power substations. This turned out to be quite neat using OpenStreetMap data. OSM lets you tag points of interest, so they just queried OSM for anything tagged with power substation within Natal, and boom, it identified the locations of 16 substations. They plotted these on the map, little cyan dots, so they knew where their key points were.
16 substations. Okay, what's next?
Step 4, build a complete graph with substations nodes. This is a bit abstract but important. Before finding the minimum connections, they first need to figure out the best possible connection between every single pair of those 16 substations using the existing road network. So they created a new empty graph just for the substations. Then for all 120 pairs of substations.
Well, 120 pairs from 16 points.
Yeah, it adds up. For every pair, they use Network X's shortest path function on the natal roadmap graph to find the most efficient driving route between them. They recorded the length of that shortest path and added that path as a single edge weighted by its length into their new substation-only graph. So now they had a graph where every substation was potentially connected to every other one, with the cost being the shortest road distance.
I see. So you calculate all the possible direct routes first, using the roads.
Exactly. And then finally, step 5. Employ Kruskal's algorithm to find the MST. With that weighted graph of all possible substation connections ready, they could just feed it into NetworkX's built-in function, nx.minimumspanningedges. It defaults to using Kruskal's algorithm, and that function just spits out the list of edges, the specific connections between substations that form the minimum spanning tree, the optimal network.
Okay. So after all that,
Yeah.
the map import, the conversion, finding substations, calculating all those shortest paths, then running Kruskal's. What was the final answer? What did it tell them for Natal, the practical bit?
Right, the payoff. The analysis found that the total length of cable needed for this minimum spanning tree, the optimal way to interconnect all 16 substations, was 46,292.2 meters, or just over 46 kilometers. That's the minimum total length required to build those crucial backup links efficiently, based on the city's actual road network. The project even produced a final map showing the substations and these optimal new connections highlighted in red.
Wow, that's actually amazing. Going from like abstract graph theory in Python code to a specific number, 46.29 kilometers of cable needed for a real city's infrastructure. That really brings it home.
It really does. It shows how this project successfully delivered on that initial challenge. Figuring out how to interconnect the substations efficiently, minimizing the cost, the actual expenditure needed. It's a fantastic example of theory meeting practice. So stepping back, what's a big takeaway here? I mean, this deep dive, it really highlights the incredible utility of applying these mathematical ideas, graph theory, algorithms, to tangible infrastructure problems. It's not just theory for theory's sake. It's about making our cities function better, more reliably.
Absolutely. And projects like this, they feed into smarter urban planning. They help build resilience into our critical systems, like power grids from the ground up. It really drives home the point that knowledge isn't just about knowing things. It's about understanding them well enough to apply them effectively. That's where the real value lies, creating systems that can handle stress better.
Yeah, and it feels hopeful, doesn't it? Seeing how we can use data and math to proactively design better systems, systems that anticipate potential failures rather than just, fixing things after they break, it seems more sustainable.
And don't forget the bottom line. Minimizing cable for 46 kilometers, that's a huge potential cost saving for the city and the utility company. That's real money that could go towards other improvements or keeping costs down for people.
Definitely powerful impacts all around. And maybe that leaves us with a final thought for you listening in. We saw how this approach optimized power connections in Natal, but think about other networks in your own life or community. Transportation systems, maybe communication networks, supply chains, even how information flows in your workplace. Could thinking about them in terms of nodes and edges and maybe finding their minimum spanning tree help solve problems or make things more efficient? It's kind of a different lens to view the interconnected world around us, isn't it?